magnets are magnets that can hold its magnetism for a long period of time. Permanent magnets include natural magnets, such as magnetite, and manufactured magnets. Most common permanent magnets are horseshoe magnets, compasses, and bar magnets. A temporary magnet is a magnet that retains only trace amounts of magnetism after magnetizing force has been removed. The most common temporary magnets are coils of wire used as electromagnets. Retentivity is a measure of the ability of a magnet to retain magnetism after the magnetizing force has been removed. Magnets are commonly used in electric motors and generators, speakers and microphones, and many industrial products. So here's in the pictures example of some natural permanent magnets and temporary magnets. Alright, with two magnets, unlike magnetic poles attract and like magnetic poles repel. All magnets have a north and south pole. The magnetic flux leaves the north pole and enters the south pole of the magnet. The basic law of magnetism states that unlike poles attract and like poles repel. The force of attraction between two magnets increases as the distance between the magnets decreases. Likewise, the force of attraction between two magnets decreases as the distance between the magnets increase. A bar magnet is surrounded by its own magnetic field that exits the north pole and enters the south pole. This can be confirmed by placing a small compass at different positions around the magnet. The needle of the compass marked in aligns with the field to point to the opposite pole. The molecular theory of magnetism states that ferromagnetic materials are made up of a very large number of molecular domains acting like molecular magnets that can be arranged in either an organized or disorganized figure. A material is magnetic if it has organized molecular magnets so that the individual fields add together. A material is non-magnetic if it has disorganized molecular magnets. Material is non-magnetic if it has disorganized molecular magnets so that the individual fields cancel each other out. The individual magnetic domains consist of many atoms or molecules that are individually aligned so their electrons all spin in the same direction. The moving charges of the electrons create a magnetic field. The electromagnetic field around a straight conductor is relatively weak and must be concentrated for use in a transformer. An electromagnetic field is concentrated by increasing the amount of current flowing through the conductor, wrapping the conductor into a coil, or wrapping the conductor around an iron core. A strong concentrated electromagnetic field is developed when a conductor is wrapped into a coil. The strength of the electromagnetic field is directly proportional to the number of turns in the coil and the amount of current flowing through the conductor. An iron core increases the strength of the electromagnetic field by concentrating the field. The left-hand rule for conductors can be used to determine the direction of the magnetic flux around a conductor. When a conductor is wrapped with the left hand with the thumb in the direction of current flow, the fingers point in the direction of the magnetic field. The direction of current is from negative to positive, and can be determined by the polarity of the source. The left-hand rule for coils can be used to determine the polarity of a coil. A coil has poles just like a bar magnet. When a coil is wrapped with the left hand, with the fingers in the direction of current flow, the thumb points to the direction of the North Pole. These rules apply only to DC, as the changing polarities of AC reverse the direction of magnetic flux twice for every cycle. Many magnetic qualities are analogous to familiar electrical quantities. You see, magnetomotive force, symbolized by MMF, is got an electrical equivalent of voltage. Magnetic flux or field flux is equivalent to electrical current. Reluctance is equivalent to resistance. And permeability is equivalent to the specific conductivity. Magnetomotive force is the force that produces magnetic lines of flux in a current as a result in a circuit as a result of current in a conductor. Magnetomotive force is like voltage in an electric circuit. Magnetic flux is the imaginary lines of force that make up the total quantity of an electromagnetic field. And that is analogous to current in an electric circuit. Reluctance is the opposition to magnetic flux in a magnetic circuit in a given volume of space or material. And that is like resistance in an electrical circuit. The magnetic field intensity is the amount of magnetomotive force distributed over the length of a magnet. Magnetic field intensity is also known as magnetizing force. Here's different units of measurement for magnetic systems. It's all a bunch of weird shit. Magnetomotive force is measured in amp turns, Gilberts, or amp turns again. Flux is measured in Webers, Maxwells, and lines. Reluctance is measured in amp turns per Weber, or Gilberts per Maxwell. Very fucking ridiculous. Yeah? Field intensity, amp turns per meter, or Orsteds. Maybe that's right.
We don't have to know all of them.
No, fuck
Okay.
no. If it's on a test, then give me. I don't want to take any one of y'all to know what a fucking Orsted is. Or a Gilbert per Maxwell.
Yeah, like I know what a nipple is, and when it comes to file size,
Flux density is measured in Teslas,
it's a form of temperature.
Gauss, or lines per square inch. And permeability is measured in Tesla meters per amp turn,
Yeah.
Gauss per
Gauss and
Orsted,
rail work very similar.
or lines per
same thing,
inch
just work
amp
differently.
turn.
Gauss is all just
Yeah.
on that.
Fucking mouth.
The rail is.
Permeability values refer to the ability of a material to conduct magnetic flux. So you see that copper does not conduct magnets very well. It's just, it's a little bit worse than air. And then say iron's got a 6,000, 8,000 permeability versus, the not even one for a copper. Permeability is the measure of an ability to, of a material to connect magnetic flux. The symbol for permeability is the Greek letter mu, which is the micro symbol. Most often permeability is actually given as relative permeability and compared to the ability of a standard material, usually vacuum or air, to conduct the magnetic flux. BH curve shows the relationship between applied magnetic force and the amount of magnetic flux carried by particular materials. Saturation is often shown on a graph of magnetic field intensity, represented by B, and magnetic flux density, represented by H. If you have a transformer or electromagnet operating near the saturation point, causes the distorted waveform. When a transformer core approaches saturation, a larger and larger amount of magnetomotive force is required to deliver increases in magnetic flux. The magnetomotive force is proportional to the current through the magnetizing coil. Therefore, larger and larger amounts of magnetomotive force require proportionally larger and larger increases in the coil current. In other words, a small increase in applied voltage will not produce the required increase in CEMF. The primary current increases disproportionately to the rise in voltage. The coil current increases dramatically at the peaks in order to maintain the shape of the magnetomotive force waveform. Proper transformer design and application allow the transformer to operate far from the saturation point to avoid waveform distortion. All right. Did y'all get all that? Y'all experts in magnetism now? Gausses and Maxwells and